Okay, chapter 10, mechanics, forces and motion. Another fairly big chapter here with lots of new ideas. So you should have already seen a little bit of vectors. Vectors are linked to this because forces can be represented with vectors as well. And the other ones here, really, this is sort of reminding you of SUVAT. And what can happen with all of this forces stuff later on is it can be combined with SUVAT equations as well. So let's start here. So I want you to try and, as always, think about a context. I want you to try and think about a tug of war. So what's going on here in terms of forces? Yeah. Well, clearly people are sort of pulling against each other, aren't they? And even though you have these forces going both ways, you might find that the rope remains in the middle. So why is this? Well, there's sort of like a cancelling out effect. So this gives us the idea that forces are only sort of half of the picture. Really, we need to know what's happening overall with forces. But we don't talk about overall forces, we talk about resultant. So this is the word that you're expected to know. We'll talk about resultant forces. So like, what's the overall impact? You know, is this like this, or maybe that's a very, very big arrow there and a small arrow? And then if the force is more, then it would start to go to the left, for example. Okay. Another really interesting idea is, let's think about if somebody's losing a tug of war. So if this has happened, well, what happens? The rope begins moving to the left, doesn't it? And then it's quite hard to stop it. Even if you are really, really pulling after a while, the rope still might move that way. So this will link to one of the ideas later that once something is moving, even if the forces are balanced, the thing wants to keep moving. You know, you have to change the forces. You have to really, really, really put in some effort, perhaps, to stop this from happening. Okay, so all of these ideas can be explained from in this chapter, and some of Newton's laws explain why we see these behaviors in the real world. Okay. So first thing we should talk about is force diagrams. So often you will get marks for doing force diagrams. You know, that can actually be the question. And even when it's not, you really need to draw these, okay? It's not an optional thing. If you don't get a correct force diagram and your assumptions are wrong, unfortunately, it will derail things later. So you need to spend a bit of time reading, thinking, sense checking that everything makes sense, that everything's there, you've used all the information, so on, and then move on with some of the harder skills. Because it's a shame to be very good at the tricky stuff, but to be let down by fairly simple things at the start. Okay, it's a really silly way to drop marks. So draw a force diagram to show all the forces acting on this block. A block of weight W is being pulled to the right by force P across a rough horizontal plane. So there's a lot of things going on there. Okay, so a horizontal plane, this is sort of like, think of it like a table or a surface or something. Okay, that's why it's got that flat line there. And the block, of course. Now, what we're doing here is we're actually modeling the block as a particle. You might remember in the chapter before, we sort of had some things that we dropped or we threw and so on. We were modeling these as particles. And although I'm drawing this as a rectangle, it's very much the same thing. Okay. Every particle has a mass. And why is a mass important? Because a mass has a weight. So a mass is just like a property. Everything has a mass. A weight is actually a force. So we're going to draw force diagrams. We need to know masses because we will be drawing weight, and weight is a force. So here is shown by W. Okay, it says a block of weight W. So you don't have to do anything because weight is already a force. It's just being drawn like that. Draw a force diagram to show all the forces acting on a block. A block of weight W, we've shown that, is being pulled to the right by a force P. So, before we move on to the force P, an obvious question here might be, if you have a block and there's just an arrow down, well, if you just pull something down, why is it not going down? Why, if something has a weight, why when you put it on a table, does it not just go through the table? Because that's what that diagram is saying to me at the moment. It's saying the thing should go through a table, which doesn't make any sense. So there's got to be something there. There must be something there, okay? And there's a reaction force. So we talk here about a normal reaction. So there's something balancing this out. Otherwise, it's like the tug of war. The thing would go through the table. So there must be something pushing it off. And in fact, in general, if you have a plane or a surface, or there are some other things like this as well, they give off a normal reaction. They stop the thing sinking through the table. Okay. And finally, we would draw on this other force that's being talked about, P. It says it's being pulled to the right. So the way I always draw my diagrams is the end of the arrow and then pointing away like that. Okay. So here is our first sort of force diagram. Is there anything else to do? Well, we haven't used this information yet as well. A rough horizontal plane. So if you have a rough surface, what's that really mean? Well, it means that it doesn't want to move. It means that there is friction. Okay. So if something is rough, we have friction. Okay. And where does friction want the thing to move? Is it helping the thing move to the right? No, it's fighting against it. So friction is going the other way. These are some of the forces that you need to get very, very familiar with. Okay. Friction is generally more of a year 13 concept. You'll look at actually being able to work out how it is. In year 12, you'll sort of just be given a number for this most of the time. But you'll be looking at weight a lot. And if you have weight, you need the normal reaction. And then there will be often some other exterior forces. So all of the arrows pointing away, force diagrams every time, please. Okay, so we've already started to talk about Newton's first law of motion, but sort of without realizing it. So what does it say? It says, if an object is at rest, it will stay at rest. And if an object's moving, it will continue to move with the same velocity, unless forces are unbalanced. Right, what on earth does this mean? Let's take a bit of time to have a think about that. So if we just have a block on a table, yeah, we know that it has a weight and we know that it has a reaction force. These are balanced. Why are they balanced? They're balanced because when forces are balanced, velocities don't change. So if something's sat on a table, it's not moving. And it will remain that way until the forces become unbalanced. So for example, if you push down incredibly heavily on it, you could change that equation there. Sorry, I'm running around trying to find some places to record today.
Don't worry, you've got it till midday, so yeah, but our mentors don't come in till then, so yeah.
Okay.
Yeah.
All right. So as we push down harder on this, we can actually change this. And what would happen if you pushed really, really hard? It could go through the table and break it. But that doesn't happen normally. Why does it not happen? It happens because the forces are balanced. Okay. Here's another one for you. So think about an object moving in space. Try and think about a movie like gravity or something like that. If the object is out there moving in space, there is gravity, but there are no obvious forces acting on it. But the thing still moves, doesn't it? Why does it move? It moves because it was already moving. And it's just going to keep doing that unless some forces make it stop or make it go faster. This idea is called inertia. In other words, like if something's already moving, it will keep moving unless you change the forces. And if something is still, then it will stay still again unless you change the forces. So this is Newton's first law of motion. It's quite tricky because it's not necessarily that intuitive, that idea that things will keep moving, even if the forces are the same. You want to say that they will stop, but that's not actually true. If things are moving and the forces are balanced, it will simply continue what it's already doing. Okay. The kind of the other side of that is that if forces are unbalanced, things will start accelerating. And you'll see later, we'll talk about this a little bit more. But if you have one force and it outbalances the other, things will begin accelerating. Okay, so we've got a quick diagram to sort of think about these forces, and I want us to have a think about the resultant force. So the resultant force sort of really means like the overall. Okay, we've talked about already that the overall impact is really what we need to look at. So let's pretend this is already drawn for us. What's happening? So we're going to look at the left and the right separately. Let's look at the left and right first, the horizontal direction. 20 to the left, this is newtons, okay? Forces are measured in newtons. 20 to the right, what's going to happen? What's the overall? Well, nothing. It's not going to move left and it's not going to move right. It's in equilibrium. It's not going to move unless it was already moving. Okay, so no acceleration, no change. The resultant force for left and right, sometimes it's written like this, is 0. What about up and down? So you have to consider vertical and horizontal separately. So up and down, you've got 30 going up and you've got 10 going down. So forces up are massively outcompeting forces down, aren't they? So we're going 20 newtons in the upwards direction. So with all of these forces, what will happen to this particle? Well, it's going to begin accelerating upwards, moving upwards, accelerating upwards. Okay, so no movement. Technically, that's not 100% correct. No change of acceleration left or right, and an acceleration upwards. So we would expect perhaps the thing to be moving upwards. Okay, so it's accelerating vertically upwards. That's what we're looking for. We need to think about the direction carefully. Yeah, we've sort of talked about that. And if there is no resultant force, so let's pretend we said here that this one was 0. Let's also pretend if this one was 0 as well, what would happen? Well, if there is no resultant force, the particle, if it's not moving, it will stay not moving, stationary, not moving. Or if it's moving already, it will continue moving at that speed. Not obvious. You need to take some time to really think about that. Okay, so this is all about inertia. If forces are balanced, it will continue to do the same velocity that it did before. Okay, so one more quick example. Vertical is 35, horizontal is 0, so the resultant force is 35 upwards. Have a quick go at these two here. So no resultant force upwards, left and right, unknown, because it's in terms of algebra, p minus 3. We don't know if that's a positive or a negative. But we know there might be some left or right movement. There certainly is no up or down movement. What do you do with multiple forces? Add them together. 7 on the left, 5 on the right. So overall, it's 2 to the left, or you could write that as minus 2. Okay, 2 to the left, you could say, is also fine. And here going down as well. So you could say it's going up by minus 2. It's just another way that you could say that. Notice here, it means that things are moving diagonally, and we will get to that a little bit later. So really, we're starting to introduce ourselves to Newton's first law, which is the idea that things will carry on doing what they're doing if the forces are balanced. If you want to change, if you want to accelerate, or you want to slow down, or something like that, you need unequal forces. That's the only way that that happens. You must draw a diagram. Weight and reaction are going to be the two most common ones at the start. Maybe some other forces can be drawn on as well. Okay, so spend a little bit of time getting really, really comfortable with those ideas, because the maths there looks very simple, but the concepts are very challenging and they are not obvious at all. If you grasp those, you'll be able to grasp much harder ideas later on.